It is my pleasure to introduce Ashley Wheeler from Mount Holyoke College, who will tell us about defining equations for matroid varieties. Ashley.
All right, thank you. Thank you for inviting me to give this talk and for organizing the series. And also thank you for coming to the talk. This is joint work with Jessica Sidman, who's also at Mount Holyoke College, and Will Travis at the US Naval Academy. And our goal is to find defining equations for matroid varieties. And by the way, I hope you're not distracted by the cat. I'll try to move her out of the way. The ground field is just C, so assume everything is over C. All right, so first I want to introduce what is a matroid before I start talking about matroid varieties. So I'm going to start with this question. Here's a matrix A, and I want to know which collections of 3 columns form a basis for the column space of A. So we can stare at this matrix and try to detect any dependencies. But there's actually a preferred thing we can do, which is to look for the non-zero 3 minors of A, because 3 columns will be linearly dependent if their corresponding determinant is 0. So I went ahead and computed all these determinants for you. If you number the columns of A 1 through 5, then each one of these tuples gives the indices of the determinant. So I computed all the determinants. And you can see that columns 1, 2, and 3 are dependent. Their determinant is 0. Same thing with columns 3, 4, and 5. And then the rest of the determinants are non-zero. So those columns are linearly independent. The matroid on the matrix A is given by the set consisting of all 3 tuples except for 1, 2, 3, and 3, 4, 5. So all the sets of indices for columns that form bases for the column space of the matrix. And then the sets in B themselves are called bases for the matroid. There's a lot of different axioms you can give in the definition of a matroid. There's the independence axioms, circuit axioms, which give a definition based on graph theory. And I think there's like 7 other equivalent definitions. But in short, matroids are a generalization of the collections of linearly independent columns of a matrix. So the axioms are set up so that way they're satisfied by a matrix. All right, so now, given a matroid on a matrix, what other matrices have the same matroid? One example would be the row-reduced form of the matrix. Because when you perform row operations, you don't change the determinants of the submatrices of full rank. But in fact, any other matrix that represents the same point in the Grassmannian is going to have the same matroid. And this is because the coordinates for a point in a Grassmannian are invariant under the left action of GLR. So doing column operations or doing row operations on the matrix doesn't change which determinants vanish and don't vanish. Are there any others? And that's the question that we're interested in. What matrices have the same matroid as a given matrix? So now I'm just going to think of the matrix as representing a point in the Grassmannian. And I'll just think of the matroid over the point in the Grassmannian and not just over the matrix. So I have this set gamma, I've called gamma, and it consists of all points in the Grassmannian with the same matroid as the matroid on the point X. And Gelfand, Goresky, MacPherson, and Serganova observed that there's a stratification of the Grassmannian by these sets gamma X. And in their paper, they give a lot of beautiful connections to polytopes and other things in combinatorics. What we're interested in is the Zariski closures of these strata. So the gamma X's are not Zariski closed. And the reason I mentioned this in the elevator pitch video is that the basis axioms of a matroid give Zariski open conditions. So saying that a determinant does not equal 0 is a Zariski open condition. So just a little notation. I'm going to let capital X denote a generic R by N matrix. And then I think everyone's seen this notation, but I just wanted to be clear. Wedge Rx is the matrix whose entries are the R by R minors of X. So we wish to find the defining ideal of a matroid variety Vx. I've called it Ix, and it's an ideal in the homogeneous coordinate ring for the Grassmannian, which you can also think of as the polynomial ring over the entries of X modulo Pluker relations. Or you can think of as the C algebra generated by these R by R minors of the generic matrix. And you'll see why I like to think of the ring in this way, as generated by minors. Unfortunately, finding this defining ideal is really hard. And these mathematicians, I think it's Mnëv and Sturmfels in their paper, use the word hell. They say all hell breaks loose, or they say it paved the road to hell and it leads to an abyss, trying to find this defining ideal. So why is this so hard? Well, as observed by Mnëv and Sturmfels, arbitrary singularities over the rationals can appear in these matroid varieties. Another reason is these Zariski open conditions, which I already talked about. And then finally, the equations are just not obvious. And I'll give examples to show that. All right, some more notation. Say A sub X is a matrix representative of a point in the Grassmannian X. And lambda is an ordered subset of the set from 1 to n of size R. Then I'm going to let brackets lambda denote the R minor of the matrix whose columns are indexed by the elements of lambda. So something in brackets refers to a determinant. Then I'm going to define this ideal in X given by all the brackets lambdas where lambda is not a basis of the matroid. This ideal is contained in the defining ideal for the matroid variety. And we use the letter N for naive ideal, because this is kind of the ideal that we want to be the defining ideal for the matroid variety. The problem is that saying that certain determinants vanish does not guarantee that the other determinants don't vanish. And so it's not clear whether or not this naive ideal actually equals the defining ideal for the matroid variety. Knudsen, and Speyer showed that the two ideals are equal when the matroid's a positroid. This is a special type of matroid where the bases, the elements of each basis are cyclic, like they're literally cyclic in the numbers. It's not clear whether or not the converse is true, if you have to be a positroid for these ideals to be equal. And then Sturmfels gave an example where these ideals are definitely not equal. So they're not equal in general. So before I go into any examples, I want to do a paradigm shift. And what we're going to do is think of matroids, instead of thinking of them as matrices or points in the Grassmannian, we're going to think of matroids as point configurations in projective space. So think of the columns of a matrix as giving coordinates for points in projective space. And I've done this for the original matrix that we started out with, A. So what I did was I literally drew the vectors given by the columns of A. and then drew the lines through the origin that they span. And then I cut those lines with the plane z equals 1. And so the intersection of a line with a plane is a point. And I get these 5 points. Each one of these points corresponds to a column of the matrix A. And I want to ask you, what do you notice about the points in relation to the matroid on A? And I've just rewritten what the bases for the matroid are to remind you.
So 1, 2, 3, and 3, 4, 5 are collinear.
Yeah, exactly. And that's not a coincidence. So 1, 2, 3, and 3, 4, 5 are the 2 3 tuples that are not bases for the matroid. And in the configuration, those are the points that are collinear. So this is an if and only if statement. Points 1, 2, and 3 are collinear if and only if the bracket 1, 2, 3 vanishes. So remember, the bracket refers to a determinant. We also have 3, 4, 5 vanishes. And the naive ideal is given by the brackets 1, 2, 3, and 3, 4, 5. Now, does the naive ideal equal the defining ideal for this matroid variety? When I first gave this example in a talk, I didn't know the answer. But then I thought about it for a couple of seconds. And the answer is yes in this case. And it's because the matroid's a positroid. I mentioned that positroids have cyclic conditions on basis elements. So that the non-basis elements, the columns are cyclic. I have 1, 2, 3, and 3, 4, 5. And so that's how I know it's a positroid. But let me give another example where the 2 ideals are not equal. So this example was given by Nick Ford in 2013. And it was kind of the inspiration for this project because he gave an additional equation in the defining ideal, not in the naive ideal, that kind of, he didn't say where the equation came from. And Jessica and I kind of puzzled over this for a while until we looked at Sturmfels' algorithms and invariant theory and realized that this equation came from a construction using the Grassmann-Cayley algebra, which I'll talk about soon. So here's the example. I call this the pencil matroid. Will said he wants to call it the pencil matroid because lines passing through a point are called a pencil, and we have 3 lines passing through a point. So the pencil matroid is the matroid with non-bases 1, 2, 7, 3, 4, 7, and 5, 6, 7. And I've drawn, the lines in the configuration are not actually part of the configuration. I've drawn them so you can see which points are collinear. So for example, in the picture, it looks like 2, 3, and 5 are collinear, but that wasn't the intention. That's why I didn't draw a line through them. So because the non-bases are 1, 2, 7, 3, 4, 7, and 5, 6, 7, that determines the naive ideal in pencil. But now here's where all hell breaks loose. The defining ideal is actually given by in pencil plus this binomial in the brackets. So this isn't obvious. How could we have known this? And the answer is by using the Grassmann-Cayley algebra, which I'll talk about next. The Grassmann-Cayley algebra is the tool that we use to extract more defining equations for the defining ideal of a matroid variety. It was originally invented and used a lot in the 70s and 80s to do synthetic projective geometry. what it does is you do arithmetic on the points in projective space, or the vectors themselves. And in this way, you obtain expressions in the brackets. The Grassmann-Cayley algebra is the usual exterior algebra over CR, but it's equipped with two operations. The first operation is called join. In P2, it refers to the line passing through points. So here's a picture of 2 points that I've labeled 1 and 2. The line joining 1 and 2 is 1 join 2, or we suppress the notation and write 1, 2. In general, the join is the span of 3 vectors. So like I said, in P2, it's just a line. Over P2, 3 points join makes a bracket. And if the 3 points are collinear, then that bracket vanishes. And you've probably noticed that the join is actually the usual exterior product, but the wedge symbol has been flipped upside down. The other operation is the meet. And in P2, this refers to the intersection of 2 lines. So here's a picture. The points are labeled 1 through 4. And we have the meet of the lines 1 join 2 and 3 join 4 is 1 join 2 meet 3 join 4. Or again, we oftentimes suppress the notation for join. The meet operation uses what's called a shuffle product. And this is how we obtain expressions in the brackets. So let me show you the formal definition of the meet, and then I'll go through an example so you can see what it really is. So for a general R, not just over P2, given 2 X tensors of step size K and L, if K plus L is smaller than R, then the meet is defined to be 0. But if it's bigger, then it's defined to be this, this sum where the vectors in the X tensors have been permuted in a certain way. So this is a really nasty, complicated definition, but it should be reminiscent of the formula for determinant, and also the general formula for Plücke relations arises in a similar way. Let me show you an example in P2 of how it works. So in the pencil matroid, we have 1 join 2 meet 3 join 4. So here's the line 1 join 2. Here's the line 3 join 4. And their meet is this point 7. So this expression in the parentheses refers to the point 7. And then 7 join 5 join 6 is equal to 0 because these 3 points are collinear. Here's how to apply the shuffles in the meet operation. This expression in the parentheses becomes 1, 3, 4, 2. And then in the next term, the 1 and the 2 are permuted. They switch places. And a minus sign pops out because that's the sign of the permutation. And then in the next step, the 5, 6 is distributed through. So you get a binomial in the brackets. And this is exactly the equation that Nick Ford gives for the defining ideal for the pencil matroid variety. Here's another example that's more interesting. It's based on Pascal's theorem, which says that if 6 points on a conic are configured in the way illustrated below, then the resulting intersection points are collinear. So I think that in the elevator pitch video, I said that the 6 points had to be on a hexagon. That's actually not quite true. That's a special case, and that's what's known as Pappus's theorem, which is a similar theorem in projective geometry. But if you look at the picture, you have these intersection points the line joining 1 and 2 intersect the line joining 4 and 5, gives a point. And then you have similar intersection points. And the conclusion of the theorem is that these intersection points are collinear. So it's a point configuration, and we have a matroid corresponding to the configuration, and a matroid variety, which I'll call V Pascal. And now I want to ask you, what is N Pascal for this matroid variety?
Is it generated by the brackets that correspond to 3 collinear, all the triples of collinear points?
Exactly. Yeah, so if you look at the picture, there's several of them. So what are some of them?
196, 172. I don't know if I'm supposed to put those in ascending order.
Yeah, you don't have to name all of them.
Okay.
Yeah, that's a good question. So 172 and 127, what's?
And that corresponds to a single column flip, so they should be minus unit multiples.
Sorry, I cut out for a second.
I was thinking that they would be opposite of each other. Oops.
I think I got booted off of Zoom for a second. Let me share my screen again.
Okay.
Okay, so I think Sean said that the generators of N Pascal correspond to the collinear points in the picture. And then the question was, well, we have a bracket 172. Is that the same thing as 127? Doesn't matter the order of the numbers that appear in the bracket. And the answer is sort of. So the brackets, remember, those refer to determinants. So if you switch 2 columns of a matrix, what happens to the determinant? Yeah, a negative sign pops out. So when you permute the entries of a bracket, negative signs pop out. But if the subspace spanned by those vectors is degenerate, then it doesn't matter if there's a negative sign or not. All right, so we don't really need to list all the brackets in Pascal. I think there are a total of 7, but you can see them in the picture. And here's our result. I Pascal is generated by at least 1 quartic, 3 independent qubits, and 3 independent quadrats in the brackets besides the brackets in Pascal. So in other words, we found 7 defining equations besides those in Pascal. And evidence, I'll just say evidence, says that these are the only defining equations. But as I mentioned, this is really hard to prove. So now I want to show you how we found the quartic, and then the other equations, we used a similar trick. So we started with the statement of Pascal's theorem, but translated into a Grassmann-Cayley expression. What it says is that 1, 2 meet 4, 5, so 7. This parentheses refers to 7. 2, 3, here's 2, 3 meet 5, 6, so 8. And 3, 4 meet 6, 1, so 9. These 3 points are collinear. So now just do the algebra, apply the shuffle product. So each one of these parentheses is a shuffle product. And then FOIL. So literally FOIL, this expression in the blue parentheses FOILs into this expression in the blue parentheses. And then finish FOILing. And you get a bunch of canceling. And the reason is because you have these brackets with repeated entries. And these equal 0. So why do they equal 0?
The repeated numbers means that the same column appears twice, so we know those have determinant 0.
Yeah, exactly. The brackets are determinants. And so if there's a repeated number, the columns are repeated. So we get a bunch of canceling, and then we get this nice 4-term quartic in the brackets. And that's one of the defining equations. Now, the proof wouldn't be complete if I didn't argue that this quartic is not already in Pascal. It really is something different. So I'm going to give the quartic a name. I'll call it F. And then to show that it's not in Pascal, it's enough to find a point in B in Pascal where F doesn't vanish. So I'm going to let Y be represented by the matrix AY, whose first 6 columns correspond to 6 points in P2 not on a conet, and whose last 3 columns are 0. So let me remind you of what in Pascal is. And notice that every bracket in Pascal involves one of the columns 7, 8, or 9. And AY was defined so that columns 7, 8, and 9 are 0. So these brackets all vanish automatically. This means that Y is in B in Pascal. But on the other hand, the first 6 columns of AY were chosen so that the corresponding points don't satisfy Pascal's theorem. They were chosen to not lie on a conet. So we can't have Y vanishing on F. Finally, I want to talk about some generalizations of the theorem. We have a generalization to more points in the Pascal configuration. In other words, we stuff more points on the conet, and each collection of 6 points out of that collection of endpoints gives a quartic. So we got equations that way. There's a generalization of Pascal's theorem to higher dimensions given by Caminata and Schaffler. And we use that to find defining equations for an infinite class of Matroid varieties. And then we also looked at Matroid varieties corresponding to configurations arising from Caylee-Bacharach theorems. So an example of a Caylee-Bacharach theorem would be Chasley's theorem. And I hope I'm pronouncing that name right. I've never known how to pronounce it. But it says that if you have 2 cubics intersecting in 9 points, and a third cubic passes through 8 of those 9 points, then it has to pass through the 9th. And Caylee-Bacharach theorems are theorems like this, where you have endpoints, and k of those endpoints satisfy some equation, then the other n minus k points have to satisfy this other equation. That's what Caylee-Bacharach theorems look like. I just want to give an example with the twisted cubic, and I think I'm doing okay on time. How am I doing on time?
I think you're doing really great on time. Got another 20 minutes.
Okay, so this might be a shorter talk then. I hope nobody minds.
More time for tea.
Yeah. All right, so here's the example. So first, I'm not going to formally state Caminata and Schaeffler's result because it's really technical and there's a lot of notation in it. But to summarize what they say is they give Grassmann-Cayley conditions for D plus 4 points in PD to lie on a rational normal curve when D is greater than or equal to 2. When D equals 2, the theorem is Pascal's theorem, along with its converse, which was proved independently by Breckenridge and Maclaurin. And then the D equals 3 case is the same theorem, but for a twisted cubic. So say you have 7 points in P3, and for each 6 tuple in 1 through 7, let J denote the point that gets left out. Then what Caminata and Schaeffler say is that the points in P lie on a twisted cubic if and only if these equations, these Grassmann-Cayley equations, are satisfied. Each of the expressions in parentheses refers to the intersection of a line with a plane. And so it gives a point. And so we have a point, meet a point, meet a point, meet a point equals 0. So this is saying that these 4 points are coplanar, is the statement. Now I actually wrote out all 7 of these equations. And the underbraces, I'll explain in a second. But like I said, so you have this one meet 2 that's a line, and then 4, 5, 7 is a plane. And so the meet operation refers to their intersection. So this is a point. And then what the underbrace is a name that I've given this point. I've called it P8. So here's P9, here's P10, P11. Why do some of these have underbraces and some of them don't? Well, the reason is because there are repeats of points. For example, this one, 2, 3, meet 5, 7, 6. That's the same point as point 9. So there are a lot of repeats, but there are a total of 21 distinct points. So let Q denote the set of points that I labeled with the underbraces. There's 14 of them. And then our theorem, or just a special case of our theorem, says let the coordinates of the points, the original points P, and then these auxiliary points Q, let their coordinates comprise the columns of a 4 by 21 matrix. And then let X denote the point in the Grassmannian spanned by the rows of that matrix. Then there are non-trivial coordinates in the defining ideal for the Matroid variety. And the coordinates look really similar to the one in the first theorem that I shared with you. So I don't think I simplified it, but this first equation, once you do all the algebra and obtain an expression in the brackets, you get something that looks like the coordinate from Pascal's theorem, except there's 7s on all the brackets. And this isn't a coincidence either. In the paper, we make the observation that that if you project from one of the 7 points in the twisted cubic, then you get a statement of Pascal's theorem. So finally, I want to talk about some other questions that we want to answer. The first one is we just want to study more Matroid varieties that arise from point configurations in classical projective geometry. So I mentioned Pappis's theorem. It's a special case of Pascal's theorem. but the configuration has a lot more collinearities in it. And the equations look like pencils of lines, like in the pencil example. And so a bunch of equations that look like the one from Nick Ford's example pop out. We also want to study Matroid varieties given by graphical matroids. So with every graph, there's an incidence matrix, and you can define a matroid on that incidence matrix. And a class of examples that gives like tractable but non-trivial matroid varieties is wheel graphs. So these are n-gons with a spoke in the middle. And then here's the hard question we want to answer. So define this other ideal J by multiplying all the brackets corresponding to bases of the matroid. So it's sort of a complement of nx, except the brackets are multiplied together. In our paper, we show that the saturation of nx by jx is contained in ix. And in fact, we show that the two ideals are equal up to radical. It can be shown pretty quickly that if n is radical, then the saturation is radical. And since n is just generated by brackets, is it easy to tell when n is radical? It's not, but one idea we had to try to study this condition is to look at algebras with straightening laws. The homogeneous coordinate ring for the Grassmannian is an example of an algebra with straightening law. So are determinantal rings. And the straightening that comes from the straightening law gives a way of writing all these expressions in determinants in a really concise way. So what are the conditions for the quotient of an algebra with straightening law by generators to also be an algebra with straightening law? Because I think that gives the condition that what you're quotienting by is radical. All right, so I want to go ahead and end there. Thank you again for coming to my talk, and thank you again for inviting me.
Cool. Let's thank Ashley. And we have lots of time for questions.
So one of the, oh, go ahead.
Do you have a guess if the positroid / naive ideal converse is true or not? Do you have a feeling, just out of curiosity? I mentioned this pretty early in the talk, but
Yeah, I think we're almost there. So you're referring to this slide? No, not this slide. This slide. So I think the converse is not true. I think that you can have the ideals equal without being a positroid.
cool.
Eloisa.
So towards the end, I think it was maybe one of the last theorems. Sorry, I'm making you move around again. There's something like you have a 4 by 21, and there are quartics. Oh, maybe it's after that. Yeah, it's after that. Maybe I already know what I'm talking about.
So this one?
Yeah. So I don't know. The 4 really like jumped at my eyes, and so I was wondering if you build these quartics explicitly, right? In this.
Yeah, and
it's like from what you said before.
Yeah, they're given exactly by those 7 equations on that slide with all the equations. So
I see.
When you multiply everything out in those equations, you get quartics.
I see. Well, so I was wondering if you know, I don't know, I see like a 4 by 21 and you're getting some quartics. So I was just wondering if there's a way of generalizing this, you know, and building like, if you have a bit bigger Grassmannian and you can get, you know, higher degree non-trivial things appearing, right? Like if you have like a 5 by something, that would be sufficient for you to come up with a fiftic, I don't know what quintic, sorry, or something like this.
So I think I see what you mean. Well, the quartics are always going to come from this Pascal condition that Caminata and Shapler generalize. The only difference is that the higher the dimension you go, the more equations pop out.
Actually, you get more equations, not necessarily higher degree things.
Right, they're always quartics.
Oh, I see. I see.
Other questions?
So were you able to determine any cubics for this example or higher degree, or are you stuck with the quartics just because there were so many?
We could extract cubics from this example. So going back to this slide, and this is how we got the cubics and quadrics in the Pascal's theorem example. If we replace this expression just with 8, so we have 8 join blah blah blah, and then that would give a cubic. And it would be an independent equation because the brackets involved in that cubic would contain 8, whereas the brackets involved in this quartic don't contain 8.
What about the quadrics? Because you had mentioned there was a quadric for the original example. Did you find quadrics? Is it also something easy to explain or not?
You do the same trick. So you replace this expression with 8 and replace this one with 9. Then you get a quadric.
Cool. Other questions?
I have a question.
Go ahead.
Do you know how these properties behave under projective duality?
That's a really good question. Because with projective duality, the roles of points and lines, at least in the projective plane, become interchanged. And so I haven't thought about this because the points that we're thinking of in the projective plane are really lines spanned by vectors. And so under projective duality, then what happens? These lines spanned by vectors become planes spanned by lines or something like that. I don't know. It's a good question. I haven't thought about it.
Thank you.
Other questions? All right, seeing none, let's thank Ashley again.